Hello, everyone. My name is Craig, and I'll be your host for today's STK virtual training. I'm located at headquarters in Exton with Jens and Shannon, who are ready to answer those questions. So if you have questions or you're falling behind, please ask using that questions panel. If you send in the question on that screen, we will see it on ours, and we will try to answer it as quickly as possible. We do have a few of you on the line, and more are logging in, so please be patient as we try to answer all questions as fast as we can. Today's training does require 11.6, and if you do not have 11.6 installed, you can use our STK web feature. It is a browser-based STK, and the details for getting that web feature up and running are in the chat panel. Without further ado, Austin, it is all yours.
Thank you, Craig. I'm going to switch over to my screen. Okay, so everyone, if you already haven't, please go ahead in the go to webinar. There's a handout. Download the recreating Apollo11.pdf. It's a continuation from last week. We added part 2 towards the bottom. So scroll down to about page 24 or so is when the part 2 starts. And if you don't have 11.6 installed, as Craig mentioned, we do offer a virtual SDK as a service, so you can do this on the web. So if you don't have SDK installed, please go to licensing.agi.com/training. That's this link up here, licensing.agi.com/training. And then once you're there, you can scroll down to where it says STK as a service. And if you're on the East Coast, select East Coast for the server. And if you're on the West Coast of the US, go ahead and click the West Coast or whatever is the closest for you. Then you can go ahead and click the Start STK Now, and a virtual desktop. You'll connect to a web instance of STK, so you have your own desktop through like the web browser. Okay, so once you have that up and running, licensing.agi.com, go ahead and open STK. And I'm going to show you how to get there. I already have it pulled up on my screen, but I'm going to show you how you can open up the scenario. So if you go up to the top of STK, you can do File Open, or if you have that pop-up box in the middle of your screen, you can do Open Scenario. Once you do that, over on the left-hand side, you'll see the STK Data Federate. That's where the scenario is saved. Go ahead and click the STK Data Federate, and then give it a moment for the connection to establish itself. And once that's happened, you'll see 2 tabs that are going to pop up with the file structure. So just give it one moment. In the meantime, let's go ahead and get ourselves on the right page. That is going to be a little bit past halfway. Part 2 is going to begin on page 21. All right. 21 of the PDF that you download, recreating Apollo 11. Okay. So once you've connected to the SDF, we have 2 tabs up here, the Search and the Browse tab. Go ahead and click on the Browse tab. From there, what you're going to need to do is expand the Sites folder, the AGI support, documentation library, virtual training, Apollo 11, and then we're going to select there's one of 2 VDFs you can select. I would recommend, if you haven't already downloaded it at this point, to go ahead and download the Apollo 11 Part 2.vdf. So that's where we ended last training with. The Part 1 is still up there. Part 2 is up there. There's also one called Part 2 with imagery, and what that is, it is the lunar terrain at a much higher resolution, but that is about 1 gigabyte in size. So go ahead and open up the smaller of the 2, Part 2.vdf, and if you want, you can use the link in the Recreating Apollo. There's a link on page 21. If you want, you can go ahead and start downloading the one with imagery separately, so you could see this. See the landing will look a lot better if you use the one with imagery, but you can follow along just fine without. So if it doesn't take too long, use the one with imagery. Otherwise, use without. All right. So that's once again in Sites, AGI support, documentation library, virtual training, Apollo 11, and we're going to use recreating Apollo 11 Part 2. All right. Once you've done that, mine's here. This is how it should load. Go ahead and click File, and we're just going to go ahead and save it locally. File, Save As. And this time we're going to save it as a scenario, and the reason for that is there are a couple different files in that scenario, and we want to access them for this training. So when you save as a scenario, it'll re-break that VDF out into its individual components, the scenario file and all the associated files. So if we scroll down to your documents, your STK user area, then click STK 1164, that's where mine is. You'll see a folder called Recreating Apollo 11 2, and if you use the imagery, it'll be Recreating Apollo 11 Part 2 with imagery. You'll click that folder, and then change the save as type to .sc. So you save it as a scenario, click Recreating Apollo 11, and then click Save. And then if it asks you to replace the existing file, just go ahead and say yes. Okay, now we have all that set up. Let's go ahead and get into it. So last time we left off, we had just gotten to the moon. They were about to separate. So the service module is above the landing location. And then they are about to separate. The lunar module is going to separate from the command service module, which will remain in orbit with Mike Collins. Neil Armstrong and Buzz will be in the lunar module. They're going to perform a small separation maneuver, and then a little bit later, they will start their descent orbit, which is a 30-second burn that lowers their paraloon down to a couple miles above the lunar surface. And then from there, they'll do about a 12 and a half minute burn, which will bring them the powered descent all the way down to the final touchdown. So that's where we're at. We're at day 4, 4 hours and 40 minutes into the mission. But before we go down to the moon, let's go ahead and set up the service module, its orbit, and lunar orbit. So if you right-click on the properties of the service module, I'm also going to pull up the PDF over here. So go ahead and open up the properties of the service module. We're going to go down to where it says, about halfway down where it says stop, move as needed. And what we're going to do is we're going to move this beneath the remove AM, which is the ascent module. So we're going to drag it down a couple segments. It was right up above training 1. And now what we're going to do is move it down to remove AM, which stands for removing the ascent module. So what we're doing now is we're going to allow the service module to propagate its entire time in lunar orbit while Neil Armstrong and Buzz Aldrin go down to the lunar surface, do their EVA, and then come back. So we're just going to go ahead and propagate the service module its entire time in orbit. That's what we're doing here. The other step you're going to want to do is click on the training button, this stop button. And then when you have that clicked, you're going to go ahead and uncheck this enabled. So we ended training 1 there. Now we're going to uncheck the stop button so it effectively gets ignored. And now we're going to go, the propagation will go all the way down to the other stop we have set up. Okay. So instead of clicking the green run button, which will run the entire mission control sequence, what you can also do as a faster way is if you click the little black drop down arrow beside it, there's this run only change segment options. Go ahead and click that. And what that'll do is it'll just continue on and not rerun the entire mission control sequence if you've already run it before. It looks like in this case, I might have the it's going to rerun everything here because the ephemeris wasn't saved with the service module. That's okay. So it's going to rerun, but if I were to run this again, it would only show run the change segments. It's just a faster way of running only the most recent part of your scenario or of your MCS instead of rerun the whole thing over and over again. So what you should see is a couple target sequences pop up. And this last one, called target docking, that should converge in 4 iterations. That is the only new thing that was added. The separation burn occurred, and now at the end of that, we want to make sure when the lunar module comes back up at the very end that it is in the right location with the surface module, so they match up once they return from the lunar surface. All right, so go ahead and close all these target sequences. The way you can do that quickly is click on the target button with a left click, and then click close all target status windows. That'll get rid of all these target sequences quickly. The other button we're going to do is click the clear graphics button. That'll go ahead and clear the graphics in the 3D window. Then you can go ahead and click OK and close this service module properties. So you'll see pretty much at this point the service module has actually turned red. That's the separation maneuver that they're doing. And then they're going to propagate for the next couple days while the lunar module goes down. All right. So we're at 4 hours, 4 minutes and 40 seconds into the Apollo 11 mission. Neil Armstrong and Buzz are about to go down the lunar module. So they have just separated. The service module has done its small separation maneuver to get where it's going to be when they rendezvous later. But let's go ahead and open up the properties of the lunar descent module. So the lunar module is comprised of 2 stages. It is the ascent stage, which comes back up from the lunar surface once they've landed and rendezvous with the command service module, and the descent stage, which is the main engine that's going to land them on the moon. So that's what we're going to model today. If you open up the properties of the descent module, what we're going to end up doing is following along the steps on page 23. And then if we open up the properties and look at the MCS, I'm just going to walk through this a little bit. What they're going to do first is they're going to separate from the service module, and then a little bit later they're going to perform the descent orbit insertion, which is a 30-second burn that's going to lower their paraloon to a couple miles above the lunar surface. So let's go ahead and model that. First off, we're going to go to the follow service module, and we're going to click on this leader section right here. We're not following the Saturn V rocket. We're going to change that. So if you click the ellipses button, we are going to follow the service module. So go ahead and change the leader to the satellite service module. And then from there, we're going to go to the joining tab right next to it. In the PDF, we have the time in which they separated, which is going to be 4 hours, or 4 days, 4 hours, 39 minutes, and 52 seconds. I would recommend just copying that directly from the PDF and go ahead and pasting it in under the joining condition. And then we're going to do after that, do the exact same thing for the separation condition. We're just going to paste that value over again. And what that means is the lunar descent module will effectively come into existence at this time, as well as immediately separate from the service module. That allows us to follow the service module up until this time, and then go on its own way. Another way that this could have been modeled, I have a note in here, is you could follow for the entire mission, but at that point you're just creating duplicate ephemeris. So if you want to be a little bit lighter on your scenario and you don't have a particular purpose, you can join at the same instant you separate. Some other things we're going to need to do is we're going to update the dry mass, and we're going to update that from the default to this new value of 6,855 kilograms. So that was the dry mass of the lunar descent and ascent modules that went down. And then we're also going to go to the tab right beside it, the fuel tank tab, and we're going to give it some new values. The maximum fuel mass, we're going to update to 8,248. And we're going to do that again for the fuel mass. So 8,248 kilograms. All right. So now we've configured the separation conditions as well as the mass of the lunar module as it's going down. So we are going to go to the target descent orbit insertion. What we're going to do now is jump into the separation burn, this target DOI, that's the target descent orbit insertion. What we're going to do for this first burn is anytime you're going to be switching central bodies or doing something with propagation that you know might be a little more intensive, you're going to want to modify your propagator. I'll cover a few more examples of what I mean by that in a little bit. But what we're doing in this case, we are no longer around the Earth, we're around the Moon, so we're going to change the propagator. So if we click this ellipses button, we're going to change that to the Moon HPOP default version 10. So we're changing from the Earth to the Moon for the propagator. And then we're going to come down to this attitude tab, and we're going to do the same thing for the thrust axes. So instead of being in the velocity normal, co-normal of the Earth, we're going to switch to the velocity normal, co-normal of the Moon. And this is towards the bottom of page 23 in the training manual. All right. You'll note that the spherical, the as and L, these are targeted. These are what we're going to be adjusting. And then the engine model, we're going to update that as well. We're also targeting thrust efficiency. So if we update the engine model, we don't want the default constant thrust in ISP. We're going to change that. And we're going to change it to, this case, the lunar descent module, custom thrust in ISP. So this has the specs of the lunar descent module, and it's not the default values. It has a 44,000 Newton thrust on it, and it has an ISP of 311 seconds. And this descent module is what's going to be used to slow the crew all the way down from moving at about 5,000 feet per second, all the way down to about 3 feet per second, a little less than 3, about 2 feet per second when they actually land. All right, so that's a little bit info about this engine model. If we go over to the Propagate tab, we're going to change the separation maneuver duration. The default is half a day. That's the default duration for finite burns. We're going to change that to be 5.2 seconds, which is how long they actually took. And then we should be good to go with this segment. So once again, as a recap, we changed the propagator 5.2 seconds. Our engine model is now the lunar module. And then for the attitude tab, we're using velocity normal, co-normal of the Moon, as well as the Moon HPOP propagator. All right, so now we've set up the separation burn. If we click the target or the segment right beneath it in the target sequence called the 2 DOI, this is a propagate segment. We're going to update the stopping condition. So if you go back to the training manual, go ahead and copy that value. 4 days, 5 hours, 36 minutes, and 14 seconds. That is the start or the initiation of the descent, the descent orbit. So it took about a little less than an hour before they actually, once they separate from the lunar module, from the command and service module, to actually go down and perform the burn that lowers them towards the lunar surface. All right. So now we've set up the segments. Let's go ahead and click on Target DOI and open up the properties of the differential corrector. What we're going to do is update the results to be the values in the training manual. So I'll show you where we got these values from. We're going to leave everything checked. I've already configured the target sequence for you, but we're going to update the values. So at the beginning of the descent orbit, they are 56.4 nautical miles. They have a flight path angle of about 0.1, which is pretty circular still. The latitude, they're at 1.1 degrees south, or negative 1.12 degrees. The longitude, they're at 140 west. And go ahead and use the values directly from the training manual, and they're moving at 5,349.9 feet per second. And then they have a heading of negative 75.7 degrees. And make sure you grab those negatives when you're copying over. But you're just going to copy those values directly from the training manual. And so we're using a very similar thing that we did in the last training. We're using these custom flight path angles and custom velocity mags. Those are all with respect to the Moon, a Moon B 1950 frame that we created last time. So these are the same calc objects that we're targeting this time. One other thing I want to point out, if we go click on the Convergence tab, one of the convergence criteria, the default is equality constraints within tolerance. In this case, it's set to either equality constraints or the last control parameter updates within tolerance. And what that means is when the target sequence is going through and it's changing the controls, but it kind of gets itself into a local minima, it'll stop changing controls very much, and you'll notice that the controls don't change very much and the desired results don't very much. If that solution's like pretty close to what you're looking for, you can use this convergence criteria, which will say, hey, I found something that's pretty close or good enough. Maybe it doesn't meet one of your tolerances almost to the exact level of precision you want, but it finds a local minimum. What you can do is set this convergence criteria to be either equality constraints, meaning my convergence or my tolerances are met, or the last control parameters aren't being updated very much anymore. They're not being updated to within this tolerance. Back on the first tab. That button doesn't even show up until you switch this convergence criteria. So for this target sequences, when we run it, it won't matter for this control convergence criteria, but when I was going through and building it in the first place, I use this every now and then. So I just wanted to point that out. So you can leave it as is, but you're just going to go ahead and click OK once you're done. All right. The next sequence, we're not going to go through and set this one up. This one's already pre-configured for you, but I want to walk through it. So after separation, about an hour later, they performed the descent orbit insertion. If you look at the descent orbit insertion underneath target descent, we already have this set up. It's going to be using the Moon default for the propagator. It's using its own custom thrust axes. It's already set up to use the lunar descent module. This thrust efficiency is a little bit lower because it didn't fire full blast for the descent orbit, and has the default, or it has a 30-second, the duration already set up correctly. So this is already pre-configured, but very similar to what we set up in our last maneuver segment. And then there are two propagates. There's a propagate to an altitude of 50,000 feet. Right after that is when the final powered descent came online. So there's two here. We have the 50,000 feet, which occurred at a certain time. And then we have about 10 seconds later, the start of the powered descent. So if I just open up that target sequence real quickly, we're not going to change anything in here, but I just wanted to look at it. We're varying the burn direction as well as the thrust efficiency, so how strong the burn is. And then we're targeting 50,000 feet when they're supposed to be at 50,000 feet. So the stopping condition is a certain time, and so we're targeting the altitude. And then there is the specific longitude value. This longitude value you won't find in the historical documents, but there was a little bit of discrepancies in the both within the historical documents, where they're changing between trajectory and lunar surface. The coordinate systems changed a little bit, so there was a little of that, as well as when we actually model the next part of the descent, if we don't get everything exactly, there's going to be slight differences. So this value that was in this differential corrector here, this 39.41, It's a pretty precise, and that is what's actually going to put us in the correct landing location. It's pretty close to the original values that are in the historical report. And I'm going to go ahead and pull that up now. So if you look at the Apollo 11 mission report, let's go ahead and maximize this guy. About halfway through on table 7.2, the trajectory parameters, they talk about where these the powered descent began, and it said it happened at 39.39 east. But the value that works inside STK with our landing sequence that we go through, as well as there's a little bit of change in the reference frames. We have a slightly different value of 39.4, but those are still very close to each other. So we're beginning our power descent slightly off of where they said, but the coordinate systems are, again, just a little confusing, so it's all honestly within pretty good tolerance there. Okay. So that's what's happening here. Let's go ahead and move this stop down to beneath the target sequence, or target descent. So we move stop down to here. And then we're going to go ahead and run the mission control sequence. So go ahead and click run. Some of those discrepancies I mentioned are actually mentioned inside the historical document itself. So they mentioned that inside the Apollo 11 mission report. They mentioned there are inconsistencies in some of the frames, and then inside of STK, there might be slight mismatches when I went through and pulled out that data and put it into STK. As well as our final approach, it's slightly different, and we'll go through. I did sort of polynomial fits for the thrust, and we're going to walk through that in detail. But that final value lined us up. When I actually recreated it in the original time for the first time, I put all of these following segments in a target sequence and changed the beginning of the powered descent longitude by a small value, so I actually landed in the right location. So the original time I went through this is this final descent sequence we're about to go through was inside another target sequence, which varied the start location, so we landed in the right spot. All right. So those two should have ran mind conversion 18 and 5 iterations. At this point, the crew are now only about 50,000 feet above the surface. So if you click the clear graphics button, then go ahead and click OK. I'm going to show this in the 3D window. You can click the stored view. That's what I'd recommend doing throughout this scenario. And then click on the stored view lunar module separation. So this happened at 4 days, 4 hours, and 40 minutes into the scenario. And the lunar module and the service module are going to separate. And this is going to happen for about an hour before they perform the descent orbit insertion. So let's go ahead and jump to the descent orbit insertion. This is a little bit different view. Descent orbit insertion happened the opposite side of the moon as the landing. They're over here on this left-hand side right now, and if I hit play or animate, you'll see the service module in a slightly higher orbit and the lunar module slowly coming down and getting closer and closer to the landing until it disappears because we haven't finished the actual landing itself. But you'll see we have a data display up here, and we're about an altitude of 50,000 feet, and we're coming down, and we're going to do is model the final powered descent.
For those of you who are wondering about the mission report, the Apollo 11 mission report, you can find that in the PDF in the handout that we have in the handout section. It's at the bottom of page 4, and there's a link to it. It says Apollo 11 mission report. You can click that, and that's what Austin just brought up a few minutes ago. So if you're looking for it, that's where it is.
Thanks, Craig. So speaking of the mission report, that's about right where the mission report kind of didn't give me any more details. It left me kind of out to dry. I didn't have any more details for the final power descent, so I had to switch over to another reference to model the final power descent. So if we switch to I have another reference here. I believe that's linked in the training manual. But what this is the mission planning for the lunar module and descent, published a couple years, I believe, after the actual moon landing, at least made public. But this was, I believe, written right after the original moon landing. So I'm going to scroll down here, and this gives me a little bit more detail of the final powered descent. So they have a picture of the pre-mission before Apollo 11, what the plan was. So the service module is going to be in orbit. The lunar module is going to come down and slowly pitch over. It'll have more abrupt phases of pitching at certain points in the mission. But really what was useful was this chart right here. And what this chart is an altitude, a descent rate, and the time of the burns, what time they actually hit these values, as well as what velocity they're moving at right now. So in the next couple sequences, I use multiple target sequences and multiple maneuvers to kind of fit the data in this table, which is it's sort of the planned profile for the Apollo 11 mission. This is what most of the Apollo 11 or most of the Apollo missions used, is a profile very similar to this one, where at 50,000 feet they kick on the lunar module descent engine, this powered descent initiation. And then what you'll see down here, if I look in this small little diagram here, we're going to look at the Apollo 11 specific one in a few moments. But what you'll see is the engine burns at about 10% or so for 30 seconds. Then it ramps up to 100% thrust. And then it drops down to about 55% thrust for a couple minutes. And then during the last, it kind of tapers off to about 20% or so for the final landing. And over in this graph right over here, we have an approximate pitch angle. And these are sort of the generic for the Apollo missions. I'm going to go to the specific one for the Apollo 11 mission, what we are going to use today. But you can see it starts off pretty much, in this case, it's about 90 degrees or horizontal to the lunar surface. And then the lunar module is pitching down. And then right after the main engine is throttled from about max thrust to about 55% or so, it'll tilt over a little more. It'll wobble a little bit to the final landing. So this table is where I got the information for most of this next sequence. So if I go back to STK and open up the properties of the lunar descent module. So we stopped where they're about to start the power descent. Here are the different phases of the power descent, that 13% that I just mentioned. They have a 93% value, approximately. Then a 56% engine thrust value, and then a low gate, which is about 500 feet. This is actually where Neil Armstrong took over and took manual control. And then two different maneuvers for targeting the final landing. So to carry on, let me actually quickly, in the Apollo 11 mission report, jump to the specific tables for Apollo 11 so you can see this data a little bit better. So if I jump to, here's an engine tab. So those are those charts I just referenced, but blown up a little bit more. This is specifically for the Apollo 11 mission. I think it's on page 182 of the actual report. It should be referenced in the training manual, the figures. But you'll see the actual thrust profile. And then the pitch flight path angle looks like this, where it starts off almost horizontal to the lunar surface and then pitches over, and it's a little wobbly, and at various phases it has more abrupt changes in altitude. And then right here you can see this is actually where Neil Armstrong took over, and it wobbled a little bit up and down. So that's what the actual mission profile looked like. If we look at this chart right here, this is not in the training manual, but this is just illustrating how I came to set this up. This is that data from the Apollo 11 mission report. What I did is I went and got something called a plot digitizer and clicked out all the points. And then in between the points, I linearly interpolate the values. So I was able to gather the data from the actual Apollo 11 mission report. So here's that pitch profile on a slightly different graph. And what I did there was I fit these polynomial second order curves to different parts of the trajectory, which correspond to this thrust profile, which is here in red. So I have both pitch angle and thrust kind of overlaid on top of each other in this graph right here. This black line is the real data. The blue line is my approximation. So I have a series of second order polynomial fits to the data. And that's how I modeled the landing inside of STK. There are a couple other approaches I tried, but this one seemed to be pretty robust and model it fairly well. So let's go ahead and jump into that. Okay, so we're going to start off in the 13% thrust phase. We're going to click on the throttle 13%. And if I open back up in the training manual, we're going to follow along the steps there. So we're going to, for this AZ knot, which is going to be the initial pitch angle, we're going to change it to be negative 104 degrees. And that just happens to line up in the coordinate system we're talking about. And then the other value we're going to use is AZ1 is this linear term, so it's degrees per second, so it's going to slowly go from negative 104 to, I believe, negative 101, because it's about a 30-second burn at the end of this. So go ahead and copy those values over from the training manual. So negative 104, 0.1 for the AZ1. We're going to do a few other things. If we click on the propagator up here, we're going to change that from the moon default to the moon 1 second. And what that is that's a custom propagator. We'll jump into that in just a few moments. But that's a moon 1 second propagator. And then we're going to change these thrust axes down here. If you click this ellipses button, we're going to change it to, instead of the velocity normal co-normal, we're going to click on the lunar descent module over here on the left-hand side, scroll up, and then look at the and select the RIC moon CBF. So what that is, it's the radial intract cross-track thrust axes with respect to the moon, and then the CBF part is with respect to the rotating moon, not the inertial axes of the moon. This is important in the last little bit of landing, otherwise you'll start getting some sideways motion. So we're going to use a radial intract cross-track, which lines up pretty well with the pitch angle, radial is up, of the fixed moon frame. Okay, so we've edited those settings here. If you click on the engine tab, the one right beside it, the engine model, the constant thrust and ISP, we're going to adjust that. So if you click this ellipses button, we're going to change it to the LM powered descent. So now we're in the powered descent phase. It's this custom engine model. Going to go ahead and select that. Then we have the propagator. That one's already looks like set up for us of 30 seconds. That's how long this burned for, I believe. Right around 30 seconds or so. So the lunar module powered descent. We have that engine model set up. Again, we're going to be targeting the thrust throughout all of these, as well as varying the azimuth. So what we changed was this 104, negative 104, 0.1, change the thrust axes, and this moon 1 second. So if I open up the properties of the differential corrector here, of this 13%, in this case, we're actually just going to run nominal, but all the rest are going to be active. The reason for this is it really didn't change very much, and then it was having a little bit of trouble getting the exact entry conditions. But if you just run nominal, it gets you pretty close. Along with that, so what we're going to end up doing for the next couple of sequences, these would all be checked, and what we're not going to check them here, but you would see the thrust efficiency as well as the pitch angle linear term, as well as a pitch angle squared term. So that's where that second order polynomial fit comes in. And what we're going to be doing for each of those segments is targeting altitude, descent rate. We're not going to be targeting the pitch angle from the actual data, but it's here as a reference. And then we're going to be targeting a velocity. And again, those values are going to come from that Apollo 11 descent profile table that I mentioned. All right, so if you just want to very briefly just look at the next couple sequences, the 93%, the 56%, and low gate, all of these are going to be a very similar setup. They're all going to be using moon 1 second, the same thrust axes, slightly different values for this start and stop because those are different polynomial fits. But they're going to be using the same engine model. So let's go ahead and grab this stop and bring it down to right above 150. But just before we run it, I want to show you what that engine model looks like, the lunar powered descent. So on your computer, if you go to your file explorer and you open up where you saved your scenario, in my case, it's my documents, STK 11, 64-bit. And then I saved it, we saved at the beginning in this, recreating Apollo 11 Part 2. I'm going to filter mine by type and then scroll down to the bottom. There are a couple there are a couple scripts in here, and these are the engine models that we use. There's also pictures in the training manual if you don't want to actually go ahead and open these files up. There's pictures in the training manual, so if you don't want to follow along with this step, you can just look at the picture. But if I open up these files, there's one called, scroll to the far right over here, Lunar Descent Engine Eval. And so that's how I actually pulled the data from the mission report and put it into the engine model. In this case, I have a list of saved times, as well as a list of saved thrust percentages. And then I'll show you, we already showed you the plot of what this looks like. That was this guy right here. That's what this plot looks like if I plot the data. But now this data is all inside of the engine model. And these we ship STK with some examples of these. There's also more examples in our code examples online. But I'm going to scroll down. This is all the configuration part where the script attaches to STK. And you can see for the outputs, we output a status, we output a thrust value, an ISP, a mass flow rate, and the input it takes is an epoch, so what time is it? And if we look at this right here, basically at each time step, each time this engine is called, it's going to go and look up the data in the table that we defined above. And it's going to linearly interpolate between the values and feed that thrust, the mass flow rate, and the ISP back to STK at each of those time steps. So that is what is being used for this 13, 93%, 56%, and low gate. So let's go ahead and run that. So if I click this green run button, and I make sure the stop is beneath low gate, let's go ahead and do that. A couple of different target sequences pop up. So during the actual mission, when they start this powered descent, they had communication issues with ground. They were oriented in such a way so their high gain antenna was having a little bit of communication issues. That was the first warning. A couple minutes before landing, they got this lovely warning that says 1202, and no one really knew what that was at first. They get this warning symbol or warning signal, and that was the computer basically saying I'm overloaded, as there was a computer overload error. So a couple minutes went by, and Mission Control got back and was like, hey, okay, this is a non-critical error. We're good to go. So it was a pretty intense moments, and I thought the Apollo 11 film that I watched recently really captured that really well. So this descent, there were a couple things that could have aborted. The communications at the beginning caused a little bit of a scare, as well as the 1202 warning signals that popped up, I believe, 4 times during the actual descent. So that occurred for the first time right around the end of this 93% burn, when the main engine was firing. Okay, so those should have all converged. At this point, I'm going to go ahead and click back on my main 3D window, and we're going to look at our stored views. If we look at the stored views, Highgate, which is 7,200 feet. So this is what it looks like at Highgate at 7,000 feet. And if I animate this scenario, you can see them coming in. There's a bunch of trajectories here. That's because I forgot to click this clear graphics button. And then if I go back to the properties and click clear graphics and click apply, that'll get rid of all those iterations it was looking at. And if I animate, you can see them coming in. And so at this point, they're getting pretty close to the lunar landing. And we're going to... At this point, it'll cut out right before the landing because we haven't modeled those last few stages here. But we get really close. We get to about 540 feet, and then it disappears because we haven't modeled that last little bit. That's when Neil Armstrong actually took over and went from autopilot to manual. So let's go ahead and wrap this guy up. If we move this stop condition, let's go ahead. We'll move it in a few moments. But if we look at the 150-foot segment and then click on maneuver, so this is Neil Armstrong. He's going to take over at about 540 feet or so, and he's going to steer the craft manually. And then I have this in state at 150 feet. If we click on, so the moon propagator is all set up. We have our estimate for our pitch angle as well as the coordinate frames we're in. If we go to this engine tab, we're going to adjust it. So if you click on the maneuver for 150 feet, we're going to click on this engine tab. We're going to change the engine. And we're going to pick the lunar module power descent to 150 feet. And then we're going to go down to the landing maneuver segment right beneath it. And we're going to do the same thing, but we're going to change it to a different engine model. If we click on the engine tab for the landing, the to landing, we're going to change the engine model from constant thrust and ISP to lunar power descent to touchdown. So those are two more custom engine model plugins, and I'm going to show you those in just a few moments. And it has a stopping condition for the very last one of an altitude of 0 feet as well as an epoch, which is when the actual moon landing occurred at 4 days into the mission, 6 hours, 45 minutes, and 40 seconds. The reason why I have that is just in case you don't want to propagate beneath a negative altitude, so that's why I have an altitude of 0 feet. And you don't want to keep propagating for a long time if for some reason it bounces back off and doesn't actually touch the lunar surface. So that's why I have an epoch stopping constraint here as well. So the two things we changed were for the to landing, lunar module power descent to landing is the engine model. And then we have a lunar module to power descent 150 feet for the maneuver above it. And then the last thing we're going to do today in terms of the MCS is scroll down to the hold. And what this is it's a segment to hold the satellite in some desired frame. So when the crew get down, they don't just touch the moon and come back off. They stay there for a little less than a day. So what this hold segment does is we're going to model that. By default, it is this hold frame in the Earth inertial. We're going to change that. So if we click this ellipses, we're going to change it to the moon fix frame. Okay, so that means once we land, we're going to stay constant in the moon fixed frame. So it's constant on the lunar surface. That makes sense. So we're going to bring the stop down beneath hold. And then let's go ahead and run the MCS. Alternatively, as I mentioned, you could just click the run only change to avoid all these pop-up windows that I saw, and it has to rerun the entire mission control sequence. You could just run the blue drop-down, which says run only change, and you'll get the same results. So if I click this target sequence right here, I'm going to close all. And then I'm going to actually just click OK on this lunar descent module here. Actually, I'm going to open it back up real quick and then clear the graphics. Forgot to do that. So I'm going to click this clear graphics button, and you'll notice there's not all these trajectories being displayed anymore, and then I'll click OK. And let's go ahead and save our scenarios. It's been a few moments since I told you guys to do that, so hit a Control S for save. And then let's watch the lunar descent module come in for the final few minutes of landing. At this point, if you didn't use the Apollo recreated with imagery, you won't see this little square right here of the final imagery. But if you were able to download the Part 2 with imagery, you should see this landing site. So I'm going to slow down just a little bit and hit play, and I'm going to start at. You can start at low gate, start at low gate, and that's about right where we were. This is where Neil actually took over and did manual control. I'm going to slow it down just a little more. Neil actually took over at this point. There's a big crater that is where the lunar descent module was originally going to land. In our trajectory here, we do something a little bit simpler. I don't have a really precise data set for his manual movements. So we do a little bit more of a smooth approach here. And you can see he also at some point pitched up to avoid this crater. He comes in and he lands right here. Ooh, I lost myself. And so they're going to land on the moon. We have 100 feet to go. At this point, they're almost running out of fuel. They're running really low on fuel. At this point, they only have about 30 or 40 seconds or so. When the time they actually land, they probably only had about 30 or 40 seconds of fuel left. So they have, at this point, less than about a minute and a half of fuel. And Mission Control gave them a warning saying, hey, you're running low on fuel. And then the last few moments when Neil landed right here next to Double Crater, and you'll see on this image set, you'll see a flag and a couple things as well. All right, go ahead and pause your scenario. So that was the moon landing and how we modeled it in STK. I'm going to cover just a few more details that I skimmed over at the end. This actual trajectory was a little more wobbly when Neil took manual control. The way we modeled it, I'm going to go into that right now. It's a little bit more smoothed out, but it's more how the nominal trajectory was planned to go, opposed to his actual hand motions. I couldn't quite get precise enough data to land him in the exact spot without doing more of a planned approach. But there's a couple different ways to model this, so if you want, feel free to give it a shot yourself. But I'm going to go over the approach I went through. So for these last two phases of the mission, there's a lunar descent engine model eval 2. And what this is it says, I want to target a descent rate and final height of 150 feet. So at the beginning of when Neil took over at 500 feet. At the end of that segment, not when he ended control, but right before the final landing, I want to be going down at about 2 feet per second or so, and then have a height of 150 feet. So what this engine model does, it's kind of a high school physics level equations here, nothing too complicated, but it says, where am I at right now? Okay, I'm in an approximately constant acceleration field, constant gravity field. What thrust do I need to be applying so that I end up at the end state of 150 feet with a descent rate of 2 feet per second? There's also a couple checks in here just in case I go past 150 feet or I get really close to it so that my thrust doesn't hit any divide by zero issues. That's what all these checks here are for. And then the final descent engine, if I scroll down here, is also a pretty simple one. It just says I want to be coming in at about 1.5 a second for the final landing, and then it'll linearly sort of increase my thrust just a little bit if I'm coming a little faster than that, and it'll decrease a little if I am coming a little slower. So it'll basically target this negative 1.5 value right here. Okay, so that's how I modeled the final approach, and that was actually originally done by the on the Astrogator Guild, one of the original developers of Astrogator. They took a very similar approach, so I followed that there, and that allowed me, if I followed more of the planned landing, to land in the actual spot they landed on. So that is going to be it for me today. If you have any questions, please send them in. We'll remain online. And thank you for attending.
Thanks, Austin. Okay, we have one more virtual training in this series, and that is going to be next Tuesday. Then we have a comprehensive crash course. That is everything that you can find in our help on help.agi.com/STK in the training book and the L2 advanced modules. Everything in that book and in that lesson walkthrough guideline. And we're going to crash it all into 3 hours. So normally it would take 2 days to do that. We're going to slam it into 3 hours in a virtual environment. It's fun, it's fast-paced, and you get to learn a lot out of it. Also, it's geared towards becoming STK L2 certified. So if you're interested in that, that's definitely a course that you would be wanting to take. We also are currently planning our virtual training summer series. So we will have a whole bunch more dates. We're thinking about probably 2 a week. So stay tuned to agi.com/training, and we'll be able to show you what we've got there. Again, the training and tutorials, if you're interested in taking your Astrogator knowledge a little bit further, you can find them in our help at help.agi.com/STK. If you have questions on something that Austin taught and we closed the webinar down and you want to ask, do not hesitate to call us up at 610-981-8888 or email us at support@agi.com. Those are really the best ways to get answers. We do get to all of them.
So one of the questions was, how does the trajectory we found, or the pitch profile that we found compared to the actual profile? So I have a plot up here actually on my screen. The black would be the historical data, which I pulled from the Apollo 11 mission report, and then how the different maneuver profiles approximated the final landing. So if I go back to the other graph, this was my, these blue arcs right here were my original polynomial fit estimates. And then here is the final converged solution that STK found. And again, there are a couple different ways to model this, but this is, in my opinion, pretty close. And you could use a series of polynomial thrusters to land on the moon. That's one way. There are, you could even use a custom pitch angle profile. You can use a couple different things, but this is the final trajectory that STK found. And also, if you were to open up the report in Graph Manager, you could see that inside of STK as well. Under the recreating Apollo 11 styles, there is this negative AZ naught, which is the pitch angle. There is a graph of that pitch angle as well. And if I were to run that till the landing time, just going to modify the dates right here. You could see those values inside of STK as well. The actual times are in the training manual, but I'm going to do an approximate right here. So you can see the pitch angle profile inside STK. This picture I have is just the original data overlaid with the values that STK found.
We're going to close this down today, and if you have any questions, you can always email us at support@agi.com or contact us on the phone at 610-981-8888. We do have the PDF available, so please make sure to download that. We also will have a recording of this video up probably later this week on our YouTube page at youtube.com/analyticalgraphics. That's where the first one is as well. We will also, because you're either in this webinar or signed up for it, we'll send a link out to remind everyone where that is. So again, thanks for attending. Hope to see you next week and at another future virtual training event. Thanks again for attending.